Hello and welcome. My name is Enobong Etuk, and I'll be talking about my time series forecasting project where I use historical data to forecast the sales of vehicles in the United States of America. So before we dive into the project, let's run through the outline. We kick off by introducing the project and the problems that the project seeks to solve. We're going to look at the specifications and design of the models that we used in the forecasting. Then we'll dive into the data. We'll look at how it was acquired. We're going to explore the data and then we're going to transform the data. We're also going to look at the motivation behind the techniques that we use to build our models and the different tunings we carried out on these models. And finally, we discuss the results. So let's get right into it. The purpose of this project was to provide reliable annual forecast for USA vehicle sales. And why is this important? Because successful demand forecasts like this could minimize lost sales and inventory costs and also help with optimizing resource allocation. How did we go about this project? Various forecasting models were built and compared using predefined matrices, and the best performing model based off of these matrices was picked for our forecasting goal. So vehicle sales account for about 3% of the United States GDP, making vehicle manufacturing an important sector. So it stands to reason why there's little to no research done on forecasting demand for vehicles. Because one of the problems faced by manufacturers is the challenge of balancing production levels, because overproducing would lead to increased inventory costs, while underproducing would lead to lost potential sales. So this project is important because it will help to accurately forecast demand, which is essential in optimizing production planning and inventory management. Going into specification and design, this project was carried out in R using some of its packages like Forecast, T Series, etc. Our data was first converted into a time series object spanning the years over which the data was collected. And then to avoid overfitting, the data was split into the training and validation sets. The models were fit on the training sets while the it was tested on 12 months of unseen data in the validation sets. We chose 12 months because our forecast goal was to predict vehicle sales for the next 12 months. We then used RMSE and MASE as our performance metrics. RMSE was primarily used to for goodness of fit on the training sets, while the MASE was used for predictive accuracy on the test sets. This project saw us use four techniques: naive, linear regression, exponential smoothing, and ARIMA to build a number of models. And based off of our performance metrics, the best performing model was selected. In the previous slide, we mentioned that one of the techniques we utilized was ARIMA. This technique can only be used on stationary time series, and as a result, we had to run an ADF test to check for stationarity in our time series. The test resulted in a p-value of 0.3, much greater than 0.05, and hence we failed to reject the null hypothesis and concluded that our series was non-stationary. As a result, we had to difference our time series ones to achieve stationarity. Our data was sourced from the Bureau of Economic Analysis. It had 591 data points with no missing values. The data spanned from January 1976 to March 2025. The dependent variable was monthly vehicle sales in millions of dollars, while the independent variable was time. So moving on to data exploration, we visualized our data utilizing a time series plot. This was done to inspect for trends and seasonality. The reason being that the presence of trend and seasonality affects the type of techniques that you would be able to use in forecasting. Also, the data source mentioned that the data was seasonally adjusted. However, an STL decomposition of our time series revealed there was still seasonality. So that means that it wasn't completely taken care of. Also, our time series has an obvious trend with fluctuating dips and recoveries. So it's a non-linear trend, and the remainder of the data just looks like white noise, which means the STL decomposition was successful in capturing most of the systematic part of the data. So once again, we get to talk about the techniques that we utilize in this project. So we will kick off with the naive model and the motivation behind selecting it. The naive model is a very simplistic model, and it also serves as a base model to measure performance. If a model doesn't do as well as the naive, then you chuck it and you move ahead with the naive model. Then for linear regression, we employed a quadratic trend model to attempt to capture the non-linear trend of our time series. Then we moved on to more complex models like the exponential smoothing and the ARIMA. The ETS was selected because the ability to incorporate seasonality and trend in the model. While the ARIMA was selected because it's a powerful tool and it utilizes past errors to improve forecast accuracy. Now we get to the interesting part where we see how well our different techniques fared when it came to fitting our training data. Not only did we look at these techniques, we looked at variations of these techniques, what you would call, we tuned these models to see how, if they would perform better with regards to goodness of fit or prediction. So we start off with the naive and the seasonal naive. From visual inspection, you can see that the naive did better than the seasonal naive. The seasonal naive here looks like our data was lagging behind it, and as such, wasn't the fit of the technique wasn't as tight as the naive forecast. Now over to the quadratic model. We ran four quadratic models. The first of which was a regular quadratic model that did not account for seasonality, and then we added sine and cosine terms to account for the seasonality to try and capture seasonality and trend in the data. And we found out that the models that had the seasonality component actually performed better both in goodness of fit and predictive accuracy than the base quadratic trend model. The difficulty in adding this the sine and cosine terms was finding a good value of t to use, which represents the period, the oscillation period. The first model we created was with an oscillation period of 12, which that's 12 months. Since our data is monthly data, it only made sense. But we ran models with different t values, and it turns out that a t value of 144, that's 12 years, was optimal. So it showed that our data had some form of economic seasonality every 12 years, which we're able to capture with the model 144. And then we combined the two models, model 12 and 144, because hey, I mean, what harm could that do? And it will be interesting to see the results at the end of the project. So moving on to more complex data, we look at some of the ETS models that we fit on our training sets. From visual inspection, there's really no difference between, the different configuration, the fits of the different configurations. However, R selected the ANN model as its optimal model. This is because R uses AIC as a performance metric, which balances complexity with goodness of fit. So we chose based off of the components, the trend and seasonal components of our data. We selected different models, AAA and MAM, to see how they fare against ours optimal model, and we'll look at the results in the coming slides. So the test results are in, and we're going to look at the different um, variations of the techniques and how they fared against each other, and then we'll also look at how the different techniques, compared to each other. So for the seasonal naive, we can see both in goodness of fit and predictive accuracy, the naive model did better. For the quadratic trend model, both in goodness of fit and the predictive accuracy, you can see that the model 144 did better, meaning that the sine and cosine terms were able to capture some of the trend and the seasonality. In the ETS model, the AAA model did better both in goodness of fit and accuracy. This also even better than ours optimal model of the ANN. It will also be worthy to note that you can see that our test data was less than the training data. This doesn't really mean that the models, work, better. It could be a sign that the training data was more complex, or rather, the test data was had lower variation than the training data and was easier. It was easier to model for these techniques. Um, so we are going to compare the ARIMA model to the AAA ETS model and model 144. We're going to look at how well their residuals to see how well they were able to capture the data, and also we're going to look at their ACF plots to see that if there's any correlation left, if there's any autocorrelation in the residuals. So, using the residuals and the ACF plots as a second filter for performance indication, and we can see that the residual of the model 144, although it was the best performing, the residual has a pattern. This shows that not a lot of the systematic part of our time series was able to be captured by the data, and if the ACF plots, there's a lot of correlation in a number of lags. So this means that this would not make a good candidate for a predictive model. So, and then when you compare the ARIMA and the ETS AAA models, you can see there's not a lot of difference both in their residuals. Their residuals are showing white noise, or what seems to be white noise. There's no pattern in there, and their ACF plots, most of is only in the lag one. Lag one shows um, autocorrelation, but the other lags, they're below the significant level. So we could say that these are favorable candidates for a forecasting model. So in conclusion, model 114, although the best performing model, didn't have great ACF and residual plots. So we look at the next best models, the ARIMA and the ETS AAA. Looking at their plots, they had good residual and ACF plots with no noticeable difference between their plots. So we have to fall back to the performance metrics that we selected. That's the test MASE and the test RMSE to get the best candidates. And with regards to those metrics, the ETS AAA performed better. So we would select that as our best performing model for the purpose of forecasting annual vehicle sales in the US. Thank you.